All right, what's up? This is linear algebra, and we're going to start off with Anki. Today's the day. We're going to get to 1.4. What is a square matrix of order n? It's an n by n matrix. Good. What is required for a sum or difference of matrices A and B to be defined? A and B must be the same size. Yep. What is the forward phase of the algorithm for solving a linear system by Gauss-Jordan elimination? The forward phase is basically introducing zeros below the leading ones. Yep. Good. What is the column row expansion of matrix product AB? Column row expansion is basically you take the column 1 of A times row 1 of B plus column 2 of A times row 2 of B plus ... plus column n of A times row n of B. So, right. Good. What is a linear combination of matrices? Essentially, it's just a combination of, it's an addition of a bunch of matrices that are matrices of the same size that all are multiplied by a scalar C, or different. They can be different C's, scalars. Cool. Assuming A and B have the appropriate sizes, how might you compute the jth column vector and ith row vector of AB without computing the entire product? To find the jth column vector, you're going to take matrix A times the jth column vector of B, and to find the ith row vector, you're going to take the ith row vector of A times B. Okay. What is the row column rule for computing the entry of AB at IJ? Row column rule is basically take the row at A, times it by the column, or you take the row I of A times column J of B, and then you add up the products. Okay. What is a homogeneous linear system? It's a linear system in which all the constants equal 0. Cool. What is the size of the augmented matrix of a linear system of m equations and n unknowns? The size of an augmented matrix of a linear system with m equations and n unknowns. Oh, that's not the right augmented matrix. Oh, n unknowns. It's going to be m times n by n plus 1. If A equals the entry at IJ, entry A at IJ, what does A22 or under sub 22 denote? It denotes the entry at row 2, column 2. What is required for two matrices to be equal? They have to have the same sizes and all the corresponding entries must be equal. Assuming, how many more of these we got? All right, we'll keep going. We got 11 more. Assuming that A and B meet the size requirement to be added and subtracted, how might you compute A plus B and A minus B? You add all the corresponding entries and you subtract B from the corresponding A entries. How many solutions does a homogeneous linear system with more unknowns than equations have? If it's got more unknowns, then it's going to have free variables. If it has free variables and it's a homogeneous linear system, then we know it's got infinitely many solutions. Suppose that A is an m by n matrix and X is a n by 1 matrix. Express A X as a linear combination of column vectors of A. Linear combination of column vectors of A. Okay, what? Suppose that we got a matrix A and it's m by n matrix, and then we got a column. Is that a column? Yeah, that's a column vector. express A times X as a linear combination of the column vectors of A. Okay. Basically, we're just going to have column vectors that are going to just go all the way down to N. No, it's going to go all the way down to M. And then at the top, it's going to go all the way over to N. We're going to split them into column vectors, and then in front of each of them, we're going to multiply it by x1, and then the second column vector is going to be x2, and then it's going to be basically dot, 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 and then it's going to be xn. All right. Yeah, that was a rough explanation, but I knew what I was saying. What is a column matrix? A matrix is one column. Only one column, that is. What are the entries of the main diagonal of an n by n matrix? A. It's basically from top left-hand corner down to the bottom right. You're going to go A11 or A sub 11, A sub 22, dot, 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 A sub nn. All right. What size requirement must be met for the matrix product AB to be defined? The number of columns in A have to be equal to the number of rows in B. What are the non-trivial solutions, if any, of a homogeneous linear system in unknowns x1, x2, and xn? The non-trivial solutions, if any, are going to be anything that where these unknowns don't all equal 0. What are the coefficient matrix and augmented matrix of a linear system? AX equals B. The coefficient matrix is going to be A and B, both in an augmented matrix. That's the coefficient matrix. The augmented matrix is going to be, no. The coefficient matrix is A. The augmented matrix is A and B. Good. What is a row matrix? It's a matrix that has only one row. If C is a scalar and A is a matrix, what is the matrix C of C times A? It's basically the matrix that results from multiplying every entry in A by the scalar C. Did we do it? Is that it? No, one more. Write out the matrix represented by the symbol AI sub ij within brackets and then sub 3, 4. So you're gonna have 3 rows and it's gonna have 4 columns, and it's gonna be A11, A12, A13, A14, and then all the way down the bottom it's gonna be, let's just say the 4th row is gonna be A41, A42, A43, A44. No, not 44. It's row 3. A31, A32, A33, A34. Okay. Boom. Now we've got like 3 more flashcards to complete for this chapter, so I'm going to go do that right now. We're not wasting any time. I'll be back in a second. We've done it. After 60-something episodes, we are done with 1.3. Yeah. All right. What do we do now? I don't even know. Just kidding. We're going to go and start flipping through this inverses and algebraic properties of matrices section. So here we go. Properties of matrix addition and scalar multiplication. Properties of matrix multiplication. Zero matrices. Identity matrices. Have yet to get to the inverses. Inverse of a matrix. Properties of inverses. Powers of a matrix. Matrix polynomials. Properties of the transpose. That's it. So we're just going to start reading, and then at the end I will come back to recall, so I'll talk to you in a bit. All right. So we just read this section called Properties of Matrix Arithmetic and Scalar Multiplication. Properties of Matrix Addition and Scalar Multiplication. Okay, that's weird. Why was it called that when we went over properties of matrix addition, which really sum up to being different forms of the commutative property, associative property, and distributive property. And that's all as they sound. Commutative property is basically a plus b equals b plus a, right? Associative property has to do with addition and multiplication, just as the associative property, commutative property both have to do with multiplication and addition. It's just like arithmetic, in which addition, multiplication both have commutative and associative properties. Associative is where you can basically, the order in which you multiply things doesn't matter if it's only a multiplication problem, or the order in which you add things doesn't matter if they're just addition. So if it's a plus b plus c, doesn't matter if you add a plus b first or b plus c first or a plus c first, you all get the same answer. And then distributive property is like when you've got some addition or subtraction within parentheses times something, you can either distribute the multiplication to both and then add them or subtract them, or you can add or subtract first and then multiply. But distributive is really, I think, usually talking about the, if it's a plus b within parentheses and then all that times c, it's talking about that equals ac plus bc. What else we got? Yeah, those are the three properties. And then it works with scalars as well, largely with these addition and subtraction and arithmetic properties. Then we went through proving the distributive property of matrices, essentially, and the way we did it was proving that the corresponding entries were equal, given that the sizes were equal on both sides. Okay, and they use column row expansion a lot to do so, to prove, to do the proof. So column row expansion, good thing we learned that, because they really didn't address it in the proof at all. It took me a couple minutes to sit there with the proof, even though it was only a couple lines, and understand what was actually going on. So good thing we went through 1.3 well, because otherwise I would be lost on that proof. Anyway, that's going to do it for today. I will talk to you later. See ya.